Okay, so let's get started. So in today's class, we meet a slightly different setup of questions and a slightly different setup of technique with respect to what you've seen so far. So as I said at the first class, supervised learning is by far the most established field in machine learning because we have algorithms, but you have a pretty good understanding of their theoretical basis and actually different ways of understanding them. Yesterday, for example, you've seen Nicolò Cesabianchi talking about sequential prediction. Here we've been introducing more the statistical learning like framework. In all these kind of settings, we do have a good understanding of how to think of what's optimal, how to tune parameters, how to design algorithm, and so on and so forth. Today we're going to move a bit beyond the pure prediction problem, the problem of predicting the output given the input. And we're going to take two different steps. The first one is going to be within an unsupervised learning setting, and it's going to be more in the direction of data exploration in a broad sense, and specifically dimensionality reduction. Okay, and you'll see in a minute what it means. In the second part of the morning, we're going to go back to supervised learning, but we're going to raise the bar a little bit. We're not going to ask about prediction, but we are going to ask about the factors that allow us to do good prediction. So the key word in the second part of the morning is going to be interpretability. We're going to try to look for models that not only predict well, but for which we can somewhat explain how the good prediction comes along given the features and the data we have. All right? So this is what we want to do next. The main protagonist of today's class is going to be PCA. So how many of you know what's PCA? All right, so we should skip this class. So PCA has many different ways to be introduced. I'm going to take a fully geometric point of view. So there's going to be almost no probability. I think, I would guess that half of you would say that PCA is something related to keeping the variance of the data. We're actually going to take another point of view and explain that in a second moment. And we're also going to try to get to the point where we can discuss extension of PCA towards nonlinear, possibly nonlinear dependence among the covariates of your data. So first of all, why dimensionality reduction? So first of all, dimensionality reduction, unlike prediction, is not such a well-defined problem, meaning that we spent some time in the first class to explain why, by assuming a model for the data, it's fairly clear what's optimal, how we measure quality of a solution given partial information, given data, and so on and so forth. This is slightly blurred, okay? It's not exactly clear what's optimal and how you would define a measure of performance. And so we will actually not indulge in much of a broad picture, but we're just going to try to give an operative definition of dimensionality reduction and then go on and jump to algorithm, which are somewhat convincing. This doesn't take much to convince yourself that it's indeed one possible way of doing it. So broadly speaking, dimensionality reduction refers to the problem of given data in some potentially high-dimensional space to map them down to lower dimension, okay? So we've seen that most of our time we like to think of data as vectors. And once maybe you have vectors that are like, I don't know, 1,000-dimensional, 10,000-dimensional, and you would like to bring them down, okay? So here there are just a couple of reasons, but there are many more. Many of you who know what PCA is, you might have seen these things called scatter plots. What are they? You take the data which are 1,000-dimensional, and we like to look at stuff. Okay? And so what you do is that you try to project data down to 1, 2, 3 dimensions so that you can actually look at them. And you plot them and you look at them. And for example, if you have images of, say, faces, you would like to see that these, in the space of 2, 3 dimensions you project them, they do form somewhat groups where, I know, my face is on one side, your face is on the other side, your face is on the other side. All right? Or some other structure. Okay? And by visual inspection, we can, infer properties of the data. And so that's one reason. Another reason is because sometimes, if you think, say, again, think of the space of images, say, 20 by 20 pixels, okay? Think of the space of faces. If you take a picture of us in the 20 by 20 pictures, and now you take the 20 by 20 dimensional space, which is 400s, probably faces are not going to fill it in, right? They're just going to be, we are not going to cover all possible values of the pixel. There's going to be some set, okay? How does that set look like? Is it a ball? Is it a star with many spikes? Is it a line? Is it a flat region? Is it a surface? Okay. These are hard questions. Okay. One slightly simpler question is: are we really covering all possible dimensions, or there are dimensions which are somewhat linked together? If you have a line, so if you're in 2 dimensions, you have a line, what does it mean? That all the values you have are related to each other, right? There is an equation that says that the 2 coordinates are perfectly proportional one to the other. That's what a line means. If you think to go in higher dimension, you might hope that something like that can happen, and that's the first assumption we're going to make. Of course, it's going to be very strong, so we'll try to get to the point where we can weaken it. But the basic idea is, if you look, for example, at my face, these pixels are not unrelated. Okay, so if this pixel has a value, this pixel is probably going to have a similar value. So this says, and probably it's not going to be linear, all right? But certainly is not just, if you look at my face in the high dimensional, as a high dimensional vector, its coordinates are going to be related one to each other. Does that make sense? So if they're related one to each other, you can ask, oh, okay, so you give me, say, 400 pixels, but truly, not all of them are independent. So these 400 dimensions are not really 400 dimensions, right? They're much less, potentially. They could be much less. And so one basic question is, how many do we have? So this question is interesting in its own right, okay, because you might think of something like the degrees of freedom of your problem, or the effective dimensionality of your problem. But in practice, it's also very important, because if you can indeed get the data down in dimension, even without losing anything, but just discovering that there is a certain amount of relationship between the pixels or whatever other coordinates you have, then you know that in some sense the high dimensionality of the problem, which is one of our main source of challenges, is actually not as bad as one might think. Okay? So in some sense, if you can postulate that whenever we're able to learn, is because data are not really high dimensional. If really we have all the time, say 400 or even more, thousands of degrees of freedom to explore, learning is probably hopeless, because we would have to have so many observations, so many examples, that it would be hopeless. So most of the time when we're able to learn, one postulates the existence of some kind of relationship. So when Francesca has been talking to you about smoothness, that's the first time you see this idea of some kind of glue between the properties of your object that simplifies them in a way. And here the idea that somewhat data are constrained to live in some kind of lower dimensional structure is another way to think about this. All right? So in the next hour or so, we try to make whatever I said now a bit more precise. So far, so good. Is the intuition roughly clear? So this is a kind of an attempt to formalize what does it mean to perform a dimensionality reduction. And so there's going to, basically, this is going to be, oh, so annoying. This is going to be the input space. There's going to be nothing else. It's going to be an unsupervised problem. There's going to be no outputs here. And let's say that I'm going to think of it as vectors, okay? Vectors in our D. And we can think of D as high. Being high. What does it mean, high? I don't know. Okay? 1,000. Depends on what kind of problem you're looking. 10,000. Certainly something you cannot look at. Even 10 could be high, actually. And what you want to do is to map all this space into some other vector space where K, the dimension of the space, actually is much smaller than D. Okay? Or even smaller or equal. Doesn't really matter. You want to go down. Okay? And even just to start to play this game, you have to say, well, I have 5 billion ways. This doesn't have to be a linear map. It can be a nonlinear map. I have 5 billion ways to do this, right? And you have to tell me how you want to do it. Well, I can give a very easy way to reduce dimensionality. Send everything in the number 2. Okay? That's a very low dimensional representation. Okay? So if you don't tell me anything else, if you just say, reduce the dimensionality, that's very easy. Okay? And so the question is, what's the other thing that you have to do while reducing the dimensionality, okay? And that's the most interesting part of the game, because that's where you make the problem meaningful. So suppose that I give you a set of data, say images, if you like, or gene expression data from patients, and you want to reduce dimensionality. What do you think could be ways to define the problem in a slightly more meaningful way? So what is the criterion that you can use to say, give me something like this with this extra property? What could this extra property be? So I slept 3 hours tonight, so you better start answering me. Unless you slept 3 hours, but you're not justified. So what we might think, you just get this bunch of points, n points in the dimension, and say, reduce the dimension, okay? And Chiara says, I want to send them all in the number 1. And you want to say, no, Chiara, you're wrong. You have to do something else. Here is my beautiful idea. Try to preserve this or that. You have to preserve something, right? Otherwise, you just throw everything away. What can you preserve? What would be something you want to do?
Something that preserves entropy of the data.
For example, okay, if you think of it as a probability distribution, you have an empirical probability distribution. I suggest maybe I define a notion of entropy, and I want, entropy gives me somewhat a notion of, we have a novel talking about this, the idea of entropy, but if you've been to high school, and I assume most of you have been to high school, you might remember that it's somewhat a measure of richness or complexity of the distribution you have. So that could be one possibility. What else?
Distance between points.
Distance between points. If everything collapses to a single point, then that's probably not a great idea. What else?
Dependence between points.
Independence. Why not? If everything collapses, again, one way is everything becomes, well, extremely dependent to each other. What else?
To be able to reconstruct the data back accurately.
To be able to reconstruct the data. What does it mean? You get the data, okay? You project them down. If the data really lie in some low-dimensional structure, you might not lose anything, actually. You might just be able to reconstruct them exactly, right? So you might actually be able to go from here to here and not to lose anything at all. Imagine that I give you points that are really two-dimensional, I give you two coordinates, but they actually lie on a one-dimensional line. If I find the coordinates of this line, I'm just able to reduce the data in one dimension, but I haven't lost anything because the other dimension in some sense was fake. Okay? And we can stop here because that's exactly the point of view I want to take. Pretty much all the other things you said give rise to other dimensionality reduction criterion, okay? You say reduce this and add this constraint, okay? Pretty much entropy, I have no idea actually, but distance preservation is pretty much what one would call multidimensional scaling. There was another one that, independence, I guess, is pretty much ICA, independent component analysis. And reconstruction is one way to look at principal component analysis in a geometric way. You will see in a minute that essentially because whenever you look at squared norm, you're essentially looking at mean and variance some way or another. There is another interpretation which rather instead of thinking about reconstruction, you talk about variance. Okay? And you say, I want to project down my data in such a way that I keep the variance as high as possible. Because if the variance of the data collapses and becomes very small, it means that is another measure like independence that says that something is getting very poor. Okay? And basically, again, whenever you take a squared norm, variance is behind the corner, or you can talk about variance or reconstruction. Okay? And I'm going to talk more about reconstruction, but I'm going to make the connection to variance. All right. So, no doubt about this. Okay? If you open the line 1, if you have to go on the desert island with one-dimensional reduction algorithm, better pick PCA because that's the one that you have to know before starting anything. It's the fundamental one for two reasons. But the main one is that in some sense, so if you want, is the simplest, okay? But it's also arguably the one that gives rise to most possible extensions, okay? In some sense, it's the least squares methods of dimensionality reduction. It's the basic methods of them all. You can then generalize, you want to make it more robust, you want to put some kind of prior, you want to make it nonlinear, but you start from this, okay? So once you know this, and you get a good grasp of what it's doing, you just need to enrich it to get something more complicated. As I said, we're not going to introduce an ideal setting and try to see how far we are from it. So we're not going to introduce a theoretical framework. We're just going to start from data and look at an algorithm. You kind of see what's the theoretical model lingering in the back, but we're not going to play that game today. So we assume that we're given data, and this is exactly the two-dimensional example. Okay, a bunch of points in 2 dimensions. And so you can think of it as a training set. Unlike the training set we've seen so far, there is no y, there is no output. It's just a pure unsupervised training set. And each of these is going to be a vector. Okay? x1 is a vector in d dimension, x2 is a vector in z dimension, and so on and so forth. So I have n points in d dimension. Okay? Boom. Is it to happen? Okay, so 30 seconds interlude of what does it mean to make projections, okay? Suppose that you have a vector. Well, I think I have a picture. You have a vector x, okay? And you have another vector w, which say it's unit norm. And you want to project this guy on this guy. So graphically, you have this vector. You just want to look at its orthogonal projection in this direction, which just means basically that you look at this vector here. Okay? So how long is this? And how can I express this explicitly in terms of x and w? So w is a unit vector in this direction. Okay? So the length is essentially going to be given by this number. Okay? X transpose w, just the inner product. It's a number. And if now I want to get this vector itself, I have to assign this length to this unit vector. Okay? So I do x transpose w, w. Everybody's happy with this? It will be useful in a minute to also remember what is the mistake we make if I give you a vector x, I give you a vector w, I ask you to project x on w, and then I ask you how much you pay if you replace the original x by its projection. Okay? So this is the original x. This is its projection, which is just this stuff. And what is the price you pay? Well, there are many ways of saying it, but the simplest one is just to take the difference between them the two, and it is going to be this quantity here. Okay? So we're going to often call this the residual of x with respect to w. Okay? This measuring how big is this vector, is a basic criterion for reconstruction. If this is 0, you're just getting the vector itself, right? If this is large, it means that you didn't get much of the vectors. If these two are orthogonal, pretty much this vector doesn't explain this at all. You good? So suppose that I give you just 1 point, and I want to reconstruct it. How should I choose w? Okay, the game is, I give you x, give me a w, they give me the best possible reconstruction. What should you do? You just get the same direction. Okay, that's the best thing. In our case, we don't have just 1 point. We're going to have a bunch. We're going to have n of them, n vectors like this. Okay, I even have a picture here. And so in some sense, we want to play the same game. So what shall we look for? This would be the measure of mistake for 1 point. Suppose that now you want to find, I ask you, find one direction, okay? We want to project everything in just one dimension, just to begin with something. And we ask, how shall we look for one dimension that best reconstruct, in this sense, all the points? How would you do that?
Minimize this sort of sum over all the points.
Right. So what you do is that you take this, okay? Whoop. You want to do it over all the training set points, and that's what you write, okay? Let me drive you to the notation, because it's very simple. This part is just what we describe. This part is what he just said. take the error you make at each point and sum them up. And then I just normalize, because it's always nice to normalize when you have endpoints. And then if you want to take this to be an empirical mean of some expectation, this is the normalization you need. And because if you don't do that, you have a spurious dependence on the number of points hidden everywhere. So it's always a good idea. Here I write a fancy notation, which is actually not so fancy, because it is just a sphere. Okay? What does it mean? When you take this direction, you want it to be a unit vector. And the sphere is the set of unit vectors. Okay? So it's a fancy way to say unit vectors. And not to have to write this stuff all the time under the minimum.
In this case, the sphere is a d minus 1 dimension.
Well, this is, again, if you think of what's a sphere, it's always one dimension low, right? Because you put the set of points on the sphere. If you take a circle in 2D, it's going to be a one-dimensional line, blah, blah, blah. So mathematically, one typically use this symbol to denote the sphere in d dimension, because the sphere in d dimension is a d minus 1 dimensional set. Does that make sense?
Yeah.
But the definition is here. Okay, so this symbol is just the notation for this set, and I'm lazy and I don't want to write it. So we're going to start, as I said, from just k, the number of dimensions we want to keep equal, and we're going to define our objective as minimizing this by picking a vector w. That make sense? We're going to call the solution to this problem, if it exists, the principal component, the first principal component of the data set. And what we're going to do next is start to rewrite this and massage it a bit, first to give it different interpretation, then to try to understand what kind of computations underlie the solution to this problem, then to see how we can make this computation better than how they look at first sight, and then how we can generalize this to go much beyond PCA. So just to build an intuition, if you have this data set, what would you think is the solution to the problem? Let's say, for the sake of simplicity, that the origin of our coordinate system is here. We're going to discuss the nature of the origin in a second. But let's assume it's here. So what do you think is the best direction I should project my data on to keep, well, to reconstruct them in the best possible way? Like that, right? Because most of the vectors are in that direction. And so if you project them, I keep most of their information. And this is purely geometric, right? It's nothing to do with, say, variance or information or entropy. It's just that if you project stuff and if you look at this seems like the good idea. Okay, so that's where we want to get at. So first of all, let us rewrite the problem in a slightly different form. We need this one step, okay? So why is this true, assuming that I didn't make a typo? You just stare at it for 1 second and tell me why it's true. How do I go from here to here? So you take the square, okay? And you get x squared. It's still here, so nothing happened there. Then I get this guy squared. This is a number, so, okay? The stuff in parentheses is a number, so you get it squared. Now you get w squared. It's a vector, so that's a norm. How much is the norm of w? All right, so I get a plus w squared here. Then I get minus this times this. But this is a number. When xi it's this is just a number. It goes in, and it just gives me twice this. So I get that number times itself. So I get x squared plus x transpose, or if you want, w transpose xi, which is the square of this, minus twice w transpose xi, which is the product of the two. That okay? Not a horribly complicated thing. Yep.
So we are basically
Yeah, put Pythagoras. We're taking the square. Yes, I guess. Absolutely, absolutely yes. But here all we are using, no, we're not using orthogonality actually. We're just using a unit norm. So we use the fact that W is unit norm. That's all. So you take this, you take the square of this, and W disappears because it's unit norm, period. So I think Pythagoras, you can let him sleep for another while. And you get this square. And then we just use the fact that this guy multiplied by this just give you this squared times 2 with a minus in front. And now if you just do the algebra, you get minus 2 plus 1, and you get minus 1. That's what you get. Okay? Okay. If you're still asleep, believe me, this is not particularly hard thing. Yep.
Shouldn't be squared.
Of course. That's where the type will come in. I just want to check if you were really listening. So it's square here and a square there. So if you now look at this, you plug it in here. Does this matter when you're minimizing over W? Not really, just a constant. The value of the minimum. So minimizer, minimum. Minimum will change. Minimizer, not really. It's just going to be the same. Okay. But here, when you plug it in, it's a minus. So if you minimize minus a function, it's the same as maximizing the function. So I can rewrite this problem just like this. All agree? Up to now, there is no reason to do this, but it's simple enough, and we just do it so that you wake up and spot my typos. Okay, the next step is, in fact, by just this little calculation, we're going to be able to reinterpret whatever we're doing, introducing the notion of variance, which so far has been completely absent from our reasoning, and it's actually one popular way to look at PCA. Let me show you the picture first. So here we thought about reconstruction, okay? But view it instead the problem in this other way. Pick a one-dimensional projection. Look at the point in that direction, okay? So if you have a bunch of points here, look at this. And now just, okay, so you got it, right? You get the point here. Now take this other one, for example. Now, I don't know, you're going to have a bunch of points here. Look at this as a distribution of points in a one-dimensional line. Which of these two distributions has a bigger variance? Right? So is this can we make this precise? Can we just use this calculation here to make sense of this? What is the connection between reconstruction and variance? Why is that just a coincidence that the direction gives you the best reconstruction is also the one for which when you project the data you get the highest variance of the one-dimensional distribution? No. And in fact, it's just that whenever you take it, as I said, when you look at this kind of stuff, there is a variance somewhere hiding. And where is it? It's here. Okay? This is almost a variance. How does the variance look like? It's something minus its mean square, right? This is something. Where is the mean? Well, the mean, it's not there because in some sense here we are not centering the data right in a way. Okay? We are keeping a one-dimensional projection, but we are putting the origin in the wrong place, so to say. Let's see what I mean by that. Assume for a minute, just to make the connection clear, that the mean, sorry, there is a sum missing here, okay? So take your input points, sum them up, and divide by their cardinality. That's the center of mass. That's the mean of your set, okay? Assume for a minute, just for the sake of simplicity, that that is 0, okay? Then when you look at this is exactly the mean. In which sense? So this is 0. You project it, and you still get 0. What you do is that now you take the projection of all these numbers. This gives you this coordinates here, W transpose x1, W transpose x2, blah, 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 blah. And now you just take this minus its mean, which is 0, square. So for each point, this is its variance in this direction. Okay? And then you just sum them up. So this is the variance of this distribution in this direction. If you change W, you take this direction. This is just, okay? So by looking at this, if you assume the data to be centered, you can just restate the problem and say, if you look at this, what you're doing is just picking up one direction so that when you look at the data in that direction, the variance of the distribution is maximum among all possible one-dimensional directions. That make sense? So now you can pick up the point of view you like the most. Okay? You can talk about picking the direction where the variance is bigger, or you can pick the geometric point of view. And you can keep on going with other perspectives, but we're going to stop here because to some extent these are the two main perspectives I think are useful. Also good? So what about the mean? Okay? Well, to some extent, what we've been doing so far was slightly wrong, and nobody complained just because I never write the reference system in the picture. But suppose for a minute that this is my data set, okay? Yeah. Yeah. I'm going to make it bigger. So look at that data set. And that is the reference system, okay? What is the principal component of this data set? The first principal component. Like this? Like this? Okay. You said like this? Or okay. So what do you think? You have to vote now. So you really have to like make this thing where it goes up. Who says is this? If you don't say this, you have to say the next one. You realize that, right? So who says is this? You. Why didn't you raise your hand? Okay, so let me make it even more clear. Okay? This is the origin. It's very far away. Okay? So, yes, this is what we want. But if you now look at the direction, this is actually, if you measure distance with respect to this, well, this is going to be the principal component, roughly speaking. Okay? Because the data are far away, and when you measure distances, this is going to look like this. This is going to look like, if you take this origin very far away, so if the center of mass of the data is very far away from the origin, this is going to look like a little cluster there, and this is just going to be the direction where you have something happening with respect to the origin. That make sense? So of course, if you don't write the origin, everything looks fine. And I have to say that the other thing is that when you start to go in high dimensions, the role of the origin, when the number of points is much smaller than the number of dimensions, it's a bit trickier. But in principle, you need to recenter. Okay? So in the variance case, this is very easy. You just basically say, look, instead of that thing I just wrote, write this one now, where x bar is just the center of mass of the points. So first of all, you compute the center of mass of the points. Then you take each point and subtract its mean, and then you project. Okay? And that's it. That's what you get. Okay? So it's this, of course, now if you define the recentered points, so if you look now at the points where you subtract the mean, you can write everything back in the same notation we did before, where this guy is now the centered variable. What if we want to take, is that clear? What if you want to take a step back and go, so this was the variance. In some sense, this is the way I wrote it for now, because I want to introduce the variance perspective. But as you understood, I actually liked to start from the reconstruction perspective. So if I want to go back now and rewind and get the perspective of reconstruction, what do you think I get? So we have to do a little calculation, okay? And if you do that in your mind, it's going to take a little bit. But just look at the geometric intuition. What we have to think about is, what we wanted to do is just to find a linear projection, which basically means that you just find a map. So you start the vectors from here, And you basically just look at the projection, okay? But what you really want to do here is what? You don't want to do this, right? You don't want to start from here and look for projections, because that's a bad idea, because this would give you, in some sense, an offset. So what do you want to do? From just pure reconstruction principle, what do you want to do? Yeah.
Maybe start from the center of mass of the data and then start finding the direction.
Yeah, so in operative terms, you first want to move everything there, which is exactly what you've done there. And then once you're here, you can keep, you can just do whatever you want to do before. So first you take the points and you put them there, and then you can play the game of just projecting. Yeah?
Does it make sense to look at this problem as if it were some kind of moment of inertia along some axis thing?
I don't know.
If you have a lot of data scattered and you're trying to find direction along with
I guess so.
there is minimum error, minimum maximum variance along the direction. You're kind of trying to find as if you had in the three-dimensional space. You had
No, I understand. But the answer is that I have no idea. And I'm a physicist, so this is particularly embarrassing. It sounds very plausible, but I hardly remember what is a moment of inertia. It happened too long ago, so I don't know. Let me think about it. It sounds like, because if you rotate something, that's probably the best direction if you look at energy and something like that. That's the other thing. Whenever you have this stuff, you can always think of this as an energy one way or another, because you're squaring something. So, but I cannot say anything better. Right, so let me go back to the other comment we were making, which was we realized that the origin here plays, and the center of mass of the data plays a special role. And what we want to do is to go from pure projection to this new stuff where we first change the origin and then we project. That's what you call an affine projection, okay? You take the data. It basically is like when you take, instead of a linear function with the zero, where the intercept is 0, you now change the intercept. Instead of taking a line that passed through the origin, you actually take a line that passed from somewhere else. And that's what you're doing, okay? So, in fact, it can be proved, and this is not too complicated, that you can rewrite. So just look at this for a second, okay? This is take the data, change the origin, project, and then re-put the origin in the right place, okay? So what you can check is that if you now ask this question, okay? So it's almost what we said, but we didn't impose the offset to be the center of mass. We say, assume that instead of a linear projection, you want to do an affine projection, okay? And now you ask two questions. What is the best slope, if you want? What is the best direction? But also, what is the best intercept, which now is a vector. It's not just a number, okay? And now you have to minimize over both. And what you can do is that you can minimize. This doesn't have to be, sorry, this is a mistake. B doesn't have to be in the sphere, okay? W has to be in the sphere. B doesn't have to be in the sphere. It just has to be, actually, its length is important. So this is in the sphere, and this is just in RD, okay? If you now look at this quantity, if you minimize over B, you can almost do it with your eyes, okay? And you can easily see that the best B is the center of mass. I don't want to do this computation because it's simple, and because the take-home message of this is essentially, look, we start with no origin to make things simple, but also because if you understand what the origin is doing, and now if you look at this, and you realize that basically the answer is the obvious one, the center of mass, then you can just go back and just ignore the center of mass and just think of this problem, okay? Where in some sense you recenter the data. And that's what I want to focus on because there is a bit more meat there. Finding the W is going to be a bit harder, but finding B is trivial. And it gives you the obvious answer. So you don't even have to do a computation. You should just remember it, okay? So if you want to do it for a minute, let me see if we can just see it. If you take this, okay, take the derivative with respect to b, that's particularly simple. It's just chain rule. And then it becomes very easy because basically it becomes linear in b. And if you use the fact that w as unit norm, blah, blah, you should get everything. Well, I don't even need, no, I think you need that actually. Okay? So let me skip this calculation. If there is any, try to do it. It should take 5 minutes. If you have a problem, we discuss. Okay? After the break, perhaps. So the take-home message here is, if you think of variance, you have, of course, to recenter the data because you need variance. If you think of reconstruction, you have to be careful where you put the origin. Otherwise, you're going to measure distances in a funny way. And so rather than a linear projection, you should really look at an affine projection. If you do that, then it turns out that the best offset you should put is just the center of mass of the data. And then at that point, all we have to worry about is W. And we can go back to the formulation we've seen before. Okay? So if you want, either this or this, where you already discounted this affine side of the story by recentering your data. Okay? So if the data are centered, it's fine. If they're not centered, we centered first, and then we play our game. And that's what we want to do next.
So would there be cases where the center of mass is not the best choice? For example, in case where the data is actually much scattered, then like in this ideal...
Depend how you how you define best choice. If you agree that you want to do this, so if you first decide that you want to do this kind of projection, and then you want to choose W and B to minimize that, no, the center of mass is the best choice for that data set. Of course, it depends on the data, but everything here depends on the data. We're not looking at what produced the data, right? But if you just look at this data and you agree that this is your criterion, the center of mass is the best thing. Okay? One generalization that you can think of doing, where you break a lot of the interpretation we are saying, but from a certain perspective you could do it, is start to basically say, oh, well, this square smells like non-robust stuff because I'm squaring here. How about I take the L1 norm or blah, 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 okay? Then a lot of the beautiful thing happens by taking squares and using linearity disappears, but that makes a lot of sense. So you could. And in that sense, then the answer would be different. And in fact, I don't know what's the answer, okay? But we're going to keep to this. And if you keep this, that's it. Okay, so reconstruction first, cheating, kind of, putting the origin in the middle of the data. Variance, realizing the importance of the center of mass, and going back to basically to the original formulation, because the center of mass, we can always discount it, okay, and discover that in some sense is the optimal problem. So the real question is, how do you find W, okay? How do you find the direction where you should project the data? And at the end of this story, you'll find out that you have to solve an eigenvalue problem, which, if you know it, you just might find it reassuringly obvious, but it's not obvious at all, because up to now, all we have is a minimization problem, and the first thing you should ask is it smooth? Is it convex? And it turns out that, in general, it might be hard. So what we're going to do instead is do a little bit of massage, and we need this one calculation. I want to rewrite the problem, okay? So we basically need one step or two to get to the point where we can realize that the solution of the maximization of this is just an eigenvalue and an eigenvector. So we need a formal step. We need a mathematical step first. It's fairly easy. So there is only one step where you have to use linearity and you have to stare at it to convince yourself you can do it. So we start from this. And then we do this amazing thing that we actually write the square as the product of two things, hoping that nobody enters the room. Then we do a pretty other amazing thing, which is we use symmetry of the inner product and switch. And this is what we get. All right? So we write it so that when I do this, you don't do like, it's obvious, okay? You just get this. Now we want to do something a little bit more interesting, which is we want to put this sum inside. But we can do that because this is an inner product, okay? And suppose that you have just to sum two of these stuff. This is let's look at what this is, okay? This is a vector. This is a vector. What is this? A matrix, okay? Rank. Rank. 1. It's a D by D matrix of rank 1. Why? Because I'm doing the outer product of one poor single vector. Okay? It's not any matrix, though. We introduced it in the first line. What am I doing here? I take a vector, W, I multiply by another vector, I get a number, and then I assign that number to this vector again. How do we call this? Very good. Okay? So basically, this matrix here is just doing the projection of that guy. So basically, you can think of that, if you rewrite it, as some matrix x plus x prime some matrix. Okay? But I can just sum them up and say, okay, look, I'm going to just put everything together. And so that's what we do. Instead of 2, we just have many, many points. All is happy? Everybody's happy? This is all the easy part. So now this is a slightly more interesting matrix. Is the sum of D matrices. Each one is D by D. Each one has rank 1, but I sum n of them. So how much is the rank of this? This is one of those tricky questions with 2 possibilities, so it depends. But it depends on what?
If the data is linear, is independent.
The what?
If the data is linearly independent.
Yeah, but that makes it a bit harder. Let's make it simple first. You have 2 possible choices, right? How big is this matrix? It's D by D. And it's a sum of how many terms? N. So there are kind of 2 obvious guess for the rank. One is a matrix which is D by D. There is a good guess of its rank. It could be D. Very good. What about the other possibility? Fn if n is smaller. You have n points, d dimension. You take all these outer products, you sum them up. And typically, the rank of this div is going to be either d or n. Now, he wants to make your life immediately complicated and say, well, if they're linearly dependent, it can even be lower than that. Okay? But certainly, if n or d is smaller, you're going to have some linear dependence. Okay? So the rank of this is always the smaller between n and d, and possibly less. So this thing here, this matrix here, is actually what one might call the covariance matrix of the data, or if the data are not centered, the second moment. Okay? Think of the data to be centered. This is exactly what you call a covariance matrix. And we're actually not going to indulge much in understanding why it's called the covariance, what values it has. It's just going to be a name for us. Okay? It's just the matrix that comes out by rewriting this. Now, if we remember that we wanted to maximize this, we found out that we actually write this problem as what one would call a quadratic form, which is exactly stuff like this. Vector, product, matrix applied to a vector. Okay? It's a quadratic form because it is like ax squared, mx squared, okay, if these were numbers. And so now, the problem of maximizing these over unit vectors, you can write as the problem of solving this problem. Okay? So now the good question is, who cares? I just rewrote the problem, okay? The first time, I bother you with taking a square, which is not much of a pain, and we just realized that we can go from reconstruction to variance. Here, we actually take a couple of steps, and we wrote the problem from this to this. Why do we want to do that? Well, to check what kind of computation we have to do. Say it again?
So the problem is convex because it's convex with everything it doesn't do.
Is it? So he said, but we don't believe him, that this problem is convex. There is a good reason why he said that, but it's wrong. Why?
Depends on the matrix, it's qualitative definite or semi-positive definite.
Very good. So he said that it depends whether this matrix is positive definite or positive semi-definite. Okay? If all the eigenvalues are bigger than 0, some are 0, it's symmetric, and so on. So
It's a covariance matrix. It's always positive definite.
very good. It's a covariance matrix. So he knows that this matrix, and you can prove in 3 lines, that this matrix actually is always positive definite or positive semi-definite. So the distinction one could make is not between convex or not, it's actually between strongly convex or not. If some eigenvalues are equal to 0, this might not be strongly convex, it might just be convex, but he said convex, so he was safe, because he only said, so if some eigenvalues are 0, he's still happy. I'm still pretty sure he's wrong, though. So the problem is not here. This is indeed a convex stuff. A quadratic form is basically, as I said, like cx squared. It's like a parabola, okay? So that's indeed convex. The problem is not that the objective function is not convex. The problem is that you have a constraint here, with the vector has to be unit norm, and this constraint makes this problem non-convex, okay? So a convex problem has to not only have an objective function which is convex, but also have to have a good constraint, and this is an equality constraint that doesn't help us, okay? So this is an important remark, because if it was indeed a convex problem, you can just start and say, look, I'm just going to go on and do my tricks and just gradient descent my way out of it. Here, a miracle kind of happened, and it turns out that the solution to this problem exists unique, and it's the biggest eigenvalue of this matrix. Okay? And basically, what happened, there are a bunch of ways of saying it. Essentially, what you do is that but this is not really a proof, okay? So I just scattered some lines that gives you an idea of how you can show this, but I don't want to show it. It's essentially, you're essentially using Lagrange theorem. You write the Rayleigh quotient, or, well, in fact, you just write this as a constraint, and then what you do is that you write the Lagrangian associated to this problem, and you can just check that essentially the solution is the biggest eigenvalue corresponding, and the value that minimizes, the vector that minimizes this quadratic form is exactly the eigenvector that corresponds to the biggest eigenvalue. Okay? One way to half convince yourself of this is taking this, adding this as a constraint with the Lagrangian multiplier, for those of you who know what the Lagrangian multiplier is, setting the derivative equal to 0, and you convince yourself in 1 second that you get exactly this. Okay? Because when you take the derivative of this guy with respect to w, you just get this. You take the derivative of this guy with respect to w, you just get this. This guy is multiplied by the Lagrangian multipliers with a minus, set it equal to 0, and this is what you get. If you know what I'm talking about, good. If you don't know, you just believe that in 3 lines you can get to this point. Okay? But then, since you're looking for the biggest lambda of them all, well, the biggest lambda is going to be the biggest eigenvalue. Okay? This is not a proof at all. It's just a hand-wavy sketch of how you go from there to there. But the good news is that the solution of the problem just reduced to find the biggest eigenvalue of the matrix and the one corresponding eigenvector. Okay? So that's good news. So far, so good. Reconstruction, variance, recentering, interlude, kind of how do you get rid of thinking about the recentering, and then manipulation to get to the eigenvalue problem. Okay? So life is pretty good, because all we have to do is solve an eigenvalue problem, forming this matrix, and so on and so forth. There are a bunch of things which are kind of annoying. One is, well, we want to do dimensionality reduction. We are doing it kind of in a harsh way, because how many dimensions we're keeping? This is just to check if somebody's awake. How many dimensions we're keeping so far? 1, okay? So the first thing we want to do is to take at least 2. The other thing we want to do is, isn't it weird that right now, if we have to compute the eigenvector of this matrix, which is n by d, suppose that I give you 10 points in a million dimensions, okay? It looks like I have to diagonalize a million by million matrix, which is kind of annoying if the rank is 10. Maybe it should be able to do something better computationally. So first thing first, how we go from k1 to k bigger than 1? We're just going to go to k equal 2 because in some sense, after that, the reasoning just iterates further, okay? And it's simple because in some sense, algebraically a couple of miracles happens and we just end up exactly with what we had so far with an extra constraint. And it turns out that instead of the first eigenvalue, you have to look at the second eigenvalue, okay? So how did that happen? So the idea is essentially the following. Consider the reconstruction point of view, okay? You took the data and you project them in one direction, okay? Now, suppose that I ask you for the second direction. What would you do?
Repeat process, discarding the first solution.
You say, I project, I check what's left, and I repeat. Right? That's what he just said. You discard what you already explained, what you already kept. You get the vector, the new vector. You know, I even have a picture, but I'm pretty sure I lazily didn't introduce it again. So I have this vector, and then I say, maybe I can look at another direction. This will do the job. In 2 dimensions, 2 is enough. Okay? So that's exactly what we want to do. Does it make sense? Direction first, check what's left, fit that. So first of all, you have to write what's left. And this is what's left. Is x minus the projection. P here is the best one-dimensional projection, okay? And this is the form of the new problem, okay? Instead of x, you write what's left. You project what's left on a dummy variable that you call w. You sum over all possible points, and then you check the best possible w, okay? But then you add the constraint, because you don't want to end up projecting this. You know, you want to say how far you want to be from the solution you already found. And the simplest thing, which is not obvious at all why you should take, but makes life much, much easier, is to take something which is linearly independent from the first direction. Okay? So you don't allow yourself, no, more than linearly independent. It's actually orthogonal to the first direction. Okay? So you don't allow yourself to do stuff like this. You actually look, say, if this was the first direction, I want to look at the other direction. Because you're already in that space, I guess so.
Yeah, I mean, you discard, because you
yeah,
collapse that data.
Independence, I think, but orthogonality probably not, right? I could take this one, right?
Well, I don't think.
So what he's saying is that by looking at the residual, you already look, say, in this direction, so you're not going to end up there again. You're going to end up in some others, but it can be any of this, I think.
Yeah.
But here we are asking to be orthogonal, to explore the other direction. This is going to give us some juice, okay? Now, do you believe this? So good? This is the conceptual part of the story. Now we just want to do some of the calculation we did before and see what happens and just check what is the, we just want to get to the new eigenvalue problem, okay? So what we're going to do first is that we're going to take the square of this and check that this is what you get, okay? This one is almost what we've done before, but hidden in R, there is W transpose X, okay? So look at this, okay? This is obvious. This is exactly what we did before. We take R, square it. Now we even have the benefit of the square. W, okay, is just a unit norm, blah, blah, blah. You just get this. Now, it's a bit of magic, the fact that if now you plug in here the definition of R, which remember is X minus W transpose W, all you get is this guy. Why? So I may repeat it because R is equal to X projected on P, the first principal component. Okay? So when I take this, all I get is this. Why is that the case? Because this is not any W. It's the W orthogonal to the other direction. So when you actually take this square, you see that stuff cancellate, and all you get is this. Okay? And again, this is another taking the square, so I think you got how you take a square. The good news now is that the part where the residual appears is only in this term, which doesn't matter if I'm maximizing over W, right? It's just a constant. It doesn't depend on W. It depends on boom, P. The first principal component, but that's already computed. I don't have to compute it again. The dependence on W is only here. This is kind of magic, okay? That come out from a one-line computation. But this is good news, because at this point, it means that we can play the same. This is not a new object. This was a new object. Here we just recovered the old object. So this problem is the same as before. So we can do all the same stuff that we did before, up to the point that we have to remember that we have this extra constraint. So it's exactly what we had before, plus this constraint. That make sense? Yes or no? Very good. Okay. And so here, basically, and this is again the step where we somewhat skip the part of the proof that shows that the solution to this problem is exactly the second eigenvector, and the value of that is the second eigenvalue. Okay? And the reasoning does iterate. Okay? So you can now basically say, let me take another W. So now I have P1, the first principal component. I know P2. And now I write the projection on P1 and P2. I define the residual. I go in there. I know that I want a direction which is simultaneously orthogonal to P1 and P2, so any linear combination of the two. Go in and do exactly the same reasoning, okay? You write this stuff. R, the only difference is that R, if you want, is going to be slightly more complicated, because here you have to take the projection over the first two principal components, P1 and P2, okay? But then you go here, you take the square, and again you will have this W is orthogonal to both P1 and P2. And so this term will be equal to this. And here you just have the residual. So exactly the same reasoning. Okay? And you will get exactly this problem where now instead of you would have a W, which is orthogonal to P1 and P2. Or if you want the eigenspace spanned by the first two eigenvector of the matrix. Okay? So here I'm voluntarily skipping one technical detail. So this is pretty much it, okay? So from now on, basically, you can look, this would be the first principal. If this is, if you have a bunch of points in here, you would have a principal component, second principal component, which would be the eigenvector, and that's it, okay? Remembering that you have to center the data at some point. Okay? So this is PCA in 65 minutes. All right. Any questions, doubts, or complaint? It's pretty much what you find. So I have to say that when I prepare this stuff, I kind of like this point of view because it's simple and it's just linear algebra and taking derivatives. There are a bunch of other points of view. One where you go straight to matrices, which is fine. It just makes life a little bit more complicated. This way you go, one dimension at a time. The other thing that people like sometimes is to assume right away, and this is something that we never do, but we could do, is assuming a probabilistic model for your data, okay? And say, if the data are Gaussian, say, then if you write down some reconstruction criteria of the probability distribution, typically what is called maximum likelihood, then you could get back something like this. So the Gaussianity will turn into the squared norm that we used, and then you have back reconstruction. In some sense here, the two things are not completely equivalent. Here we just take a geometric point of view. We are not assuming the data are Gaussian, okay? But we are just assuming that we want to look at reconstruction. So and if you want to look at reconstruction, you have one direction first, and then you have to keep on going.
If you fit a multivariate Gaussian to the data, actually the parameter of the Gaussian is the covariance matrix.
Mm-hmm.
We can see geometrically as the principal eigenvalues.
Right, right. And if you want, that's exactly, perhaps that's the best point of view. One thing is saying my data are Gaussian, and so I'm going to derive computation from it. One thing is say I want to fit the Gaussian to my data. God knows what my data are, okay? But I want to fit the Gaussian. Why? Well, because it's simple, because the first thing I want to do, and so on and so forth. That's exactly what we're doing here, if you want, okay? And then by putting a Gaussian instead of minimizing minus an exponential, you maximize blah, blah, that's exactly what you get. Okay, so the point I want to make is just that rather than assuming data to be Gaussian, in some sense, if you want in your terms, you're fitting a Gaussian. And this is just equivalent to say that you want to look at L2 reconstruction. Before I said instead of an L2 reconstruction, you could look at some other kind of reconstruction, say an L1 reconstruction. And in that perspective would be that instead of fitting a Gaussian, we would fit another exponential distribution with some other I don't know, for example, a Laplacian distribution or something like that. Okay? And in fact, one direction which I'm not going to describe, and if you want comes from that point of view, is why don't we add other constraints? So we want reconstruction, but we want also the vector to be nice in some way. Okay? You could also do that. And I'm not really going to discuss that. Then you get stuff like sparse PCA. We'll meet sparsity in a little bit. And you can view that as putting extra prior on your distribution and so on. I don't emphasize this duality much because to some extent, I don't know, in my head there is a lot of convergence of ideas. And this one I think is a bit simpler. Other comments? Yeah.
So the eigenvalue problem is the eigenvalue decomposition of the covariance matrix.
Yes.
And then, like you have written here, the principal components are equal to, like, the first principal component is the first eigenvalue times the first eigenvalue.
The first, yes.
Yeah, and then the second, and so on.
Yep.
So the eigenvectors are not the same as the principal components, but they're in the same direction.
No, you call the eigenvectors to the principal components.
But then here you have is U1 the first eigenvector.
Yeah, but you... Yeah, in fact, I don't even know who calls what. So I call, and I think the rest of the work called the eigenvector the principal component, which is length 1. And then if I ask how long is long the principal component, or how much is the reconstruction, the variant, you go in that direction. So, because remember, the solution to the problem is just the direction, because we put the unit norm assumption. So the length is actually the value of the reconstruction. See, is the mistake I make by projecting data in this direction. Okay? And so this is the length of the vector, is the eigenvalue. And this one is the mistake I make after projecting on the first and second eigenvector. So that's what's left. So typically, I think the eigenvector is called the principal component, and that is the associated residual. Okay? In fact, it's not quite the residual because we still have to, if you remember, this is just the max part, which has this extra term. We still have to do the sum. There is this part, okay? If you want to get the actual reconstruction, the overall residual, you still have to sum these terms to this guy. So the eigenvalue will give you this part. You still have to add this part if you want the actual reconstruction error. All right? Okay, so how much does it cost to do this little game? Well, full disclosure, we don't know. Okay, it's an open problem in complexity theory how much it costs to do an eigenvalue decomposition. But if you look at numerics, typically you would say that if you have to do the composition, it costs you, say, d cubed. And if you just have to find k eigenvalues or an eigenvector, it's roughly going to cost you this much. Okay? That's, if you ask people in the street how much is this computation, that's roughly speaking what they would reply. All right, is this the complexity of the problem? Is this the main complexity of the problem? Well, where did the number of points end up? It disappeared. How is that possible? Well, it's not possible. The point is that I have to build the covariance matrix first, right? And if you think of the covariance matrix is just another way of writing it is take the data matrix, which is n by d, transpose it, and multiply by itself. So this is a n by d, d by n. What's the cost of this? I have to multiply vector of size n. I have d vectors here and d vectors here, so I have n times d squared. Okay? So that's exactly where n enters when you form the matrix. Now, which one is bigger?
Hopefully n.
Yeah. Well, hopefully for sure, right? Because well, yeah, we don't know because it can be one bigger than the other. So depends if n is bigger than, well, I don't know in fact. But typically this one is the dominating term. I'm getting lost. So k d. So if if n is smaller than d, then k will be for sure smaller. If n is bigger than d, then this could be d cubed, whereas this one is still nd squared, so it's still true. So I think this is the leading term. But I slept 3 hours, so don't quote me on this. All right, so can we do better than this? Okay. Can we do any better than this? So if n now is much, much smaller than d, we're still paying quadratically in the number of dimensions, and only linearly in number of points. So it feels not just. If n is much smaller than d, what I would want to do is to invert the role of d and n somewhere. Okay? I would want to have something which is linear in the dimension, which is the biggest parameter, and perhaps quadratically in the smaller of the two. Okay? So how do you do that? Well, and the other question I generalize. So what you do is that you just remember what's an SVD, okay? Which roughly speaking is the following thing. So the simplest version we want to think about is if you have a matrix like this, okay, you can build this square matrix, or you can build the other square matrix, which is the one which is n by n. The good news is the eigenvalues of these two matrices are the same. The vectors cannot be the same, because one matrix is d by d, the other one is n by n. So they just don't have the same size. But you can go from one to the other. Okay? And this is basically what an SVD is. So it's the composition of a matrix in three matrices. One is an orthonormal basis. So suppose that I take the k eigenvalues. So I want to look at k eigenvalues. What I'm going to do is that I'm going to get a basis of the Rn, or the vector of size n, not all the space, of a subspace of dimension k, because I'm taking only k eigenvectors. So I take k vectors of size n, and this is going to be an orthonormal basis for some subspace of size k. Same, I'm going to take k vectors of size d, and this is going to be some eigenspace for a space in Rd. And then I get a diagonal matrix. I wrote here, I think this is called what's it called? The compact SVD. I don't remember. You can also write it in a different way. I always write it like this. So the point is that the number you put there, that's the diagonal matrix, are not quite the eigenvalues of those guys, are the square root. Okay? Now, the way I actually like to write the singular value, which turns out to be completely equivalent to what I just wrote. Okay? The one I wrote is much more compact, but actually I like to write these four equations instead, because they are more explaining. So what they say is, if you build so let's first look at these two guys, okay? This one here is exactly the covariance matrix written in matrix form. And this one here is the other guy. I call it K because that's what we usually call a matrix made of inner product, because we think of it as a kernel matrix. The rest of the world would call it a Gram matrix, okay? So this is the D by D guy, and this is the N by N guy. Now, these are the four equations of SVD. The first one says, look, the eigenvalue of this problem are the same as the eigenvalue of this problem. Here, the eigenvector I'll call P, and here I'll call U. How do I go from P to U, or to U from P? Well, you have to apply the right X or X transpose to this vector. So, for example, if you take P, which is size D, you apply the matrix N by D to it, and you don't get U, you get U multiplied by square root of lambda J. Okay? If I give you U, which is of size N, you now apply the transpose of this, and you get Pj up to this scaling factor. If you want to play 1 second with this, you will check that this one equation is equivalent, completely equivalent to these equations. Okay? Where this are related to the matrix V, and the U are related to the matrix U. Okay? So one is the column of one, and one is the column of the other. So these are K vectors in Rn. These are K vectors in Rd. And these are exactly them. These are those K vectors in Rn. These are those K vectors in Rd. And they're related by this equation. Okay? What I care about here are two things. The first one is, well, it's actually one thing. Let's ask the question again. I give you 10 points in a million dimension. Can you compute the first principal component with a complexity which is smaller than nd squared? Well, let's check. This kind of suggests that there is another way. Okay? The first way is build this and diagonalize it. That's a straight way. But now we have these 4 equations. And in particular, we have an equation that says, if you want to look at this eigenvalue, you can first do that, and then use this, right? Think a second about it. And then somebody take full courage and tell me in words what's the procedure. You see what you have to do? So I give you the matrix X. Is 10 by a million. I ask you to compute P, but you don't want to build the matrix C because it's too big. It's a million by a million. What do?
You do singular value decomposition of the data matrix Xn instead of the for to compute then the.
Bear with me just 1 second. Let's say that you don't have the SVD command. You just have the eig command. Okay? So let's just do eigenvalues, just to use this equation because I just want to make it operative. But that's correct. So what you said is take the SVD of this, and then you use it some way. But just bear with me 1 second. Let's say that instead of an SVD, you want to take an eigenvalue decomposition, okay? So you build this, okay? How much does it cost? Well, we have to move the transpose from here to there, right? How much does this cost? The vectors are of size d, and I have n here, n here. I have to multiply them. So this is n square d. Okay? Fair enough. Now I build the matrix Kn, and I have to diagonalize it. How much does it cost? Well, before we said that it costed to diagonalize this for k eigenvectors, essentially cost kd squared. This one here is going to be kn squared. All right? So we're good. That's exactly what we want to do. Almost. Because once you finish diagonalizing this, you don't have p, right? You just have u. And u is n-dimensional. So now you have a 10-dimensional vector. You don't have a million-dimensional vector, which is what you want to do to project your data. You just have a 10-dimensional vector, which is the eigenvector of this. So what do? Well, you search for an equation that can help you. Which one is it? This one here. This one says, give me u, apply x, and I give you that guy. Or if you want, you have to divide this number by the eigenvalue, the square root of the eigenvalue. How much is this operation? So it is x transpose u. How big is this? How big is this? This is dn. So now I have to multiply vector of size. And I have how many of them? So it's dn, or nd. Okay? And this is a negligible complexity with respect to the other ones. Okay, then we're good. Okay? If you have many more dimensions than points, you just essentially use the idea underlying SVD. And this is just one way to tell you the story behind SVD. And this is what you get. I like to write it this way because in a minute you'll see that this allows us to go from linear PCA to nonlinear PCA in 7 minutes. So that's it, okay? That's what we just said. We don't want to repeat it. Stare at this equation for a minute and tell me you're fine with this. Here it just is in vector notation. This is the uj vector. So it's the uj eigenvector, the corresponding square root of the eigenvalue. And here is the matrix notation. Here I just write this as multiplication of the columns and the columns of this, rows of this. Okay? And this is what you get. What are this? These are the entries of this vector. You fix uj, it's one vector, and then these are its components. First component, second components, and so on. So what you do is that you take the row of the data matrix, and you assign to them this length. Okay? Just a change of notation for now. It will be useful in a second. Okay, so I'm going to use this notation now. So what we want to do is to go beyond. So what did we do here? We're basically saying, look, if you want, we're taking the Gaussianity assumption. But if you want, the other essentially thing we're doing is looking at linear subspaces. So we take one direction, then we take another direction, and we span a plane. And then if you go in another dimension, we'll span a cube, but it will be a hyperplane somewhere. Okay, it will be a linear thing. Suppose that I give you now data that lie on something like this, a semicircle. Well, they won't do it, right? So suppose that your data look like this. What is the first principal component? And let's assume that the origin is somewhere here. Well, it's this, and then you have that. But this is really, as you're saying, it's like fitting a Gaussian to something which is not Gaussian, right? You're fitting a plane to something which is not a plane, or a line to something which is not a line. So can we go beyond that? Well, one way is to use kernels. And this is the idea. Instead of looking, what was the question? No. Instead of looking at the principal components themselves, what we want to do is to look only at the projection induced by the principal component. And we will see that while the principal component can be very high dimensional, in some sense, if you're able to compute the projection in a good way, we're good. We want to use kernels for that. So remember that this was the projection, or the projection coefficient. Okay? What I want to do now is apply this projection to this point X transpose. Okay? So I want to do X transpose Pj. This is what I have, right? I just write an inner product. So yes. And then you just basically rewrite this as a sum and use linearity. And that's what you get. Okay? So right now we don't have the time to go slowly through this, but this is just linearity of the inner product again. Now, if you look at this equation now, you see that it smells like kernel stuff, because you only have the inner product here. The stuff that you're going to compute are eigenvalues and eigenvectors of size n, and then you're going to use this equation. So the idea here is pick a transformation of your data, okay? Some kind of feature map. For example, in the case of a function like this, you can use a quadric and just explicitly, instead of just taking the coordinate of your vector, you take the square of the coordinate, the product of the coordinate, and so on. And you map in this much higher dimensional space with all these extra numbers. In that space, you play the PCA game. So if you do that, you can convert, instead of x, what you're going to get. Everywhere, instead of x, you're going to get phi of x. Okay? And then the rest, you just play the same game. Okay? Only if you want, rather than be in the original space, you're in this other space. And here, this doesn't matter. Okay? There's nothing to do. These are recycled pictures. But the point is that you do PCA in this new space, and you get exactly the same equation. You just get this. Okay? Where this is just the inner product, and the matrix Kn is just given by this. I call this sigma, but this is really just lambda, what I called lambda before. Okay? So this is just the kernel matrix. Good? So, is that okay? Again, the abstraction here is that you have to take a feature map, okay? And somebody has to give you the feature map. But if you have the feature map, you go into, you compute it, you go in the new space, and then you just do what you've done before, okay? And the computation will be the same as before. If it's a finite dimensional feature map, you add d dimension, you go higher, maybe to d square or d cube dimension, and then you project down. What you gain is that instead of a linear projection, you're now looking at a nonlinear projection in the regional space.
This is after calculating the eigenvalues.
No. So the procedure is, you get the data, you pick a feature map, and you assume that you have the feature map. You can compute it for each point for 1 second, okay? Then you compute this matrix. You pick the eigenvalue of this matrix and the eigenvectors. You get now the point x. You cannot compute the principal component explicitly, but you can compute the projection associated with the principal component, and it's given by this equation. So depends when you want to start the game, okay? The first thing you do is that you get the feature map, then you do the eigenvector, and then you use this equation. Make sense? No?
Yeah, it's funny because we are going to an upper dimensional space to go down to.
Absolutely. That's exactly a good point. So what you do is that you take your coordinates, you explode them to basically get, in some sense, you explode them so that you can get this new coordinate where you can explain. Think about it this way. You want to explain no linear relationship by looking at the linear method. So what you do is that you explode in this high dimension where things are, the numbers are obtained through nonlinear operation. But then you look at linear relationship. But you look at linear relationship of nonlinear stuff. Okay? That's kind of the trick. And that's the weird thing. Because in some sense, you are in love with vector spaces, because that's the only place where we know how to compute stuff. And we make this effort to go in high dimensions, to allow us to go beyond linearity. That's exactly what you do. Okay? And the last step here, because we are done, is that if now you have a feature map that you cannot compute explicitly, but is given by a kernel, doesn't matter. Because this is where you want to use the kernel, and this is where you want to use the kernel. So you can use the Gaussian kernel, say. You shove it in here and shove it in there. And that's it. Okay? And it's the same picture, just instead of using quadric, you're using this Gaussian embedding. And so it's a bit more abstract. Okay? All right, let's stop here, and we reconvene in half an hour.